the motion of a pendulum is going to look like here. Okay, so I'm going to start with this one, and I'm going to use this one. We're not going to do some of the forces because pendulums, they rotate. So what's a better thing to do? Torques. Let's do that. Yay! All right. Okay, so let's draw our pendulum. And if we're going to do torques, we better define the distance here and some angles and do our free body diagram on here. So let's see. I'm going to call this distance here the length to the center of mass. And I'm going to define this angle theta. Okay, now if I'm doing torques, what do I have to define? Reference points, absolutely. So I'm going to call this guy A. And I also need to talk about, well, I'm going to define the positive direction to do this way. Okay, so what forces do I have acting on this mass here? Gravity. Anything else? Tension. Okay, so let's do our sum of the torques around point A. And what that's going to equal, just like some of the forces always equal MA, some of the torques are always going to equal the moment of inertia about point A times alpha, which we can write as theta double dot. Okay, what are my sum of the torques? Let's see, what torques do I have acting on here? Does tension give a torque? Nope, because it looks like the angle between R and F is 180, and so that's going to give a cross product of 0, so we don't have to worry about that one. What about gravity? Sure. Okay, so it looks to me like if we go from a pivot point to gravity, and we have to bend to gravity, oh, that's going to give me something that's rotating this way, which is in the negative direction. So I'm going to have negative, let's see, the distance is LCM, cross the force is mg. Okay, now I have to pick the perpendicular component. It looks like if I extract this out here, it's going to give me, what do you think? I'm thinking that's looking like a sine theta, so let's go ahead and do that. Okay, so this doesn't look to me like it's going to end up being simple harmonic oscillations. Why? Yeah, there's this nasty sine theta thing here, and that's just not, you can't really separate that out so nicely. Okay, so you guys were from Frosh Lab. We asked you to take the period as a function of angle. We said you might really want to focus on the small angles and see what happens. Let's see. If we have theta is really small, what happens to sine theta? Yeah, it's approximately equal to theta. And you can actually get that by plugging sine theta into the Taylor series and taking the lowest term, you'll end up getting sine theta is approximately theta. So if we put that in here, we get minus LCM mg theta is approximately equal to I about point A, theta double dot. This is looking much better. Now it looks like I can rearrange this guy and make it look like my simple harmonic motion equations. Theta double dot plus LCM mg over the moment of inertia at point A times theta equals 0. Awesome. This looks, what is this? My omega squared.
But then it's just G over LCM.
Oh, okay. So you're saying, well, when is it? Somebody said this is G over LCM. Well, it depends on what this moment of inertia is. I didn't really say what kind of object this was I was swinging on the pendulum, right? So length of our motion, limit that theta is really tiny. We could do EDT equals 0, but in the interest of time, I think we're just going to do the sum of the torque. Okay, so we end up with this answer for omega, but as was very astutely brought up, what if this thing is a point mass? Well, let's see what happens. So, all right, no, I'm not that tall again. All right. Okay, so we have omega equals the square root of mg LCM all over the moment of inertia at point A. If this thing's a point mass, then what's its moment of inertia? ml squared, and what's LCM? It's just L because it's a point mass, right? So the distance to the center mass is just the distance, is the length of the string. All over ml squared. That looks like that's going to simplify down to G over L. And let's see, the period, which is what you guys measure in Frosh Lab, is 2 pi over omega, which is just going to be 2 pi square root of L over G. Yay! Is that what you guys got? Awesome. Okay. So you see that simple harmonic motion is just really not just springs. Sometimes, though, you have to make approximations near certain points. Motion is not strictly simple harmonic for all ranges, but if you look at a certain area, you can make nice simplifications.